Perhaps you were wondering about number 83 on page 240. Let's find the maximum volume of a right circular cone inscribed in a sphere radius r. So, here's a sphere radius r, and there's a right circular cone inscribed. And clearly we can make a bigger volumed cone inscribed in the green sphere just by dragging that pink base down a bit. And what if we went past the equator with that base? The base is going to get smaller at that point, but we're also getting a higher cone, so maybe the extra height will outweigh the smaller radius of the circular base. And maybe somewhere between the equator and somewhere down here is the place where the cone would be at maximum volume. So how do we find the volume of a cone? It's 1/3 times the area of the base times the height. To maximize this, we are going to take the first derivative with respect to one variable. So we can't have two different variables which are changing. The radius of the cone is actually x in this problem, and so we can't do the derivative to find the maximum value yet, because we can only do that if the volume was a function of a single independent variable, not two different variables. So we'll need to make a substitution here somehow or another. How might we do that? Well, the height of our cone we can see is this dimension plus this dimension. And this one is from the center of the sphere to the top. So we can break up h into the radius of the sphere plus this dimension. How can we represent this dimension? Well, we do have a right angle here. We know that this is x, and we know from here to here is the radius of the sphere. So that is the radius of the sphere. And now we can find out what this is going to be. That unknown leg squared plus x squared equals the hypotenuse squared. So that unknown leg squared is the square root of r squared minus x squared. And now we can express the height of our cone as the radius of the sphere plus that dimension. All right, so now we can rewrite the formula for the volume in terms of only one variable, x. There it is. Remember, r is actually a constant. It's the fixed radius of the original sphere. All right, we're ready to do the differential calculus on this to do the optimization problem and find the maximum volume of this right circular cone inscribed in the sphere, a sphere of radius r. All right, the derivative with respect to x of the left side and the right side. We'll factor out that pi over 3 factor, which is a factor of the entire thing, so we can factor it out. And then we'll use the product rule, the derivative of the x squared times the second factor plus the derivative of the second factor, which is the square root of r squared minus x squared, times the first factor. So the derivative of x squared is just 2x times that factor, and the derivative of the square root is 1/2 times that difference to the negative 1/2 times the derivative of the inside, which is negative 2x, right, and then multiplied by the other factor. All right, the 2 divided by 2, so we're left with minus x cubed times this in the denominator to the 1/2, the square root. All right, and we'll find the optimal values of the volume when we find out when this first derivative of volume is equal to 0. Obtaining common denominators and then combining those fractions. Now this fraction is equal to 0 only when the numerator is equal to 0. So let's solve the equation. Numerator equals 0. just combining those like terms. Now let's factor out a negative x from everybody. So we get that, and this red factor times the black factor is equal to 0, so either red or black is 0. It can't be this one. If x was 0, wouldn't make sense in this problem, so that's an extraneous solution algebraically. So we're going to have to solve the black one. If the black factor is set equal to 0, we could add 2r root of this difference to both sides, so that the 3x squared minus 2r squared stays on the left, and that goes to the right. Now, why would we want to do that? To solve this, we're going to get rid of the square root sign by squaring both sides. And now that the square root term is isolated, things will work nicer that way. We'll square this binomial, square this factor, so 2r squared is 4r squared, and the square root of that expression is the expression. These terms will cancel each other out. All right, adding 4x squared r squared, or 4r squared x squared to both sides. 4 of them and negative 12 of them is negative 8 of those r squared x squareds. And remember, r is a fixed constant for the sphere's radius. We're trying to solve for x. Factoring out the GCF of just x squared. And now if x squared times the group is 0, either x squared is 0, which doesn't help us, or the group is 0. All right, remember that our variable is x, everything else is a constant. So let's go ahead and add 8r squared to both sides. Divide both sides by 9. And x is the square root of 8r squared over 9. We only talk about the positive root because we're talking about a greater than 0 dimension of the cone. And so we have 3 in the bottom, r on top, and the square root of 8. Or 2r root 2 over 3. To prove this is the x value which maximizes the volume, we can just do the first derivative test. We can look at the sign of v prime before that critical number and after. And we'll use this expression for determining the sign of v prime. This is v prime. So this factor is positive, so when this difference is positive, the sign will be positive. When this factor is negative, it'll be negative. All right, so if we take some value to the left of this critical number, let's take a value that's really close to 0. That would be to the left of that critical number. If x is really close to 0, we're subtracting a really tiny fraction. For one, if x was 1,000th, for example, x cubed would be 1/1,000,000,000th. And r is a fixed radius, so if the radius is bigger than 1, we're subtracting a really tiny fraction. So this is going to be a pretty big number that we're taking the square root of, and the denominator making this even smaller. So when x is close to 0, this is super, super tiny. This is going to be a lot bigger because it's 2 times that x value instead of that x value cubed. And then we are multiplying it by a radius plus another positive value. So we can see pretty clearly that when x is to the left of this, the derivative of v with respect to x will be positive. Using the same sort of logic, if we took a value bigger than this value, let's take something extremely big like 100 or 1,000. Here we'd have like 200, and this expression is staying pretty fixed, although this radical expression is getting smaller as x gets bigger. But we're subtracting that big x value over here, like 100 or 1,000, and that's getting cubed. And so the second part of the difference is getting bigger than the first part, and that would be negative. So the rate of change of the volume is positive and then negative, which means this will be a relative maximum of the volume. When x is this value, the volume will be a relative maximum. Okay, so our cone has an x and an h, and we know the x value that's going to maximize our volume. It's 2r root 2 over 3, where r is the radius of the original sphere. Recall that h was defined as the radius of the sphere plus this dimension of that right triangle, which we determined was the square root of r squared minus x squared. So the height of the cone was r plus that expression. Well, we know what our x value is now, where we maximize our volume. It's this. When we square that and subtract from 1r squared, we get a ninth r squared. Taking the square root of that, we get r over 3. R plus r over 3 is 4/3 r, and therefore the maximum volume of an inscribed right circular cone is 1/3 times pi times the radius of the base of the cone squared times the height of the cone, which we determined has a maximum volume when the radius of the base of the cone is 2r root 2 over 3, and the height of that cone is 4r over 3. Which means, finally, if we have a sphere radius r, and the biggest right circular cone that can be inscribed will have a volume of 32 pi times the square of the radius of the sphere divided by 81 cubic units. And recall conceptually that this cone won't be maximized when it's at its maximum area of a circular base. We'll maximize the volume of the cone when the circular base is a little smaller than the great circle of that sphere. When the height of the cone is actually 1 1/3 times the radius of the sphere. So it's pretty cool that the maximum inscribed cone is exactly 1/3 extra of the radius of the sphere in height. Will there be a question that's this long on the test Monday and Tuesday? No, there won't be one that's this long.